Okay, hello everyone. In a new video, so we have reached part 13 of chapter 5, which is the chapter of kinematics for grade 11 students. So also in this part we are going to solve some exercises as a direct application on what we have explained previously. They are telling me the center of inertia G, which is the center of mass, of a solid S is moving on a circular trajectory of a radius r is equal to 2 meters. Then we have that the radius r is equal to 2 meters. The angular abscissa of G is given by theta is equal to this. So notice that the angular abscissa is given by theta, where the curvilinear abscissa is given by S, okay? So here, because we are discussing a circular motion, let me write on the scratch the different types corresponding for the circular motion that are given by UCM. So we have that UCM is given by theta is equal to omega t plus theta 0. Omega is equal to a constant and alpha is equal to 0. Whereas in the case of UVCM, we have that theta is quadratic in time. In which omega is equal to alpha t plus omega 0 and alpha is equal to a constant. Okay, so now let's get back to the question. And notice that here in part 2 they are mentioning the curvilinear abscissa. So let me write also the different relations between the curvilinear and the angular. As for the linear and angular quantities, we know that S is equal to r theta, V is equal to r omega, and A tangential is equal to r alpha. Okay, and okay, so let's proceed. Now in number 1 they are telling me give the nature of motion of the solid S, and the nature of motion is identified by referring to the given form. So we have that since theta is equal to 6.28 t plus 1.57, so notice that here the angular position is linear in time. Whenever the angular position is linear in time, this means that the type of motion is UCM. Verifies the general form. Then the type of motion is UCM. So now we can use these equations in addition to these, okay? So no need for these equations in this exercise. Now in number 2 they are telling me write the equation S, write the time equation S is equal to f of t of the motion of S. So notice that we have theta. We are interested in determining S. S is given by r multiplied by theta. The value of r is given by 2. And the value of theta as function of time is given by this. So this is given by 2 multiplied by 6.28. So this is given by 12.56 t. And 2 multiplied by 1.57. This is given by 3.14. So S as function of time is given by 12.56 t plus 3.14. So this is S as function of time. So this is S of t. Now in number 3 they are telling me to calculate the angular speed, which is omega. Notice that since the type of motion is UCM, then we have that theta is equal to omega t plus theta 0. Omega is equal to a constant in which alpha is equal to 0. And we have that theta is equal to 6.28t plus 1.57, which means by comparison that comparing linear terms, we have that omega is a constant which is equal to 6.28 radians per second. So omega in this case is given by 6.28 radians per second. And in the same part, they are telling me to deduce its linear speed. Its linear speed corresponds to v. So v in this case is given by square root of vx square plus vy square. We don't know the x component and the y component. However, we know v as function of r and w. So in this case, simply the speed will be given by r multiplied by omega. So 2 multiplied by 6.28. So this is equal to 12.56 meters per second, because everything is expressed in the SI. So V is equal to 12.56 meters per second. Now in part 4, they are telling me calculate the period of the motion of S. So in addition to these formulas, we know that omega is equal to 2 pi f, which is equal to 2 pi divided by t, and t is equal to, or let's say f is equal to 1 over t. We are interested in determining the period, knowing that we know the value of omega. Notice that omega and the period are related via the following equation. So omega is equal to 2 pi divided by the period. Then the period is equal to 2 pi divided by omega. So the period is equal to 2 pi divided by omega. The value of omega is given by 6.28. The value of pi is given by 3.14. Now plugging this fraction on the calculator, then the period is given by 1. Since everything is expressed in the SI, then the value of the period will be in the SI, which is seconds. So period is equal to 1 seconds. Now in the same part, they are telling me to deduce the frequency. The frequency is simply given by 1 over the period. So 1 over 1, which is equal to 1 Hertz. So the frequency is equal to 1 Hertz. Now in part 5, they are telling me calculate the angular acceleration. So simply alpha is equal to 0 and the reason is given by UCM. Then deduce the tangential acceleration. We know that the tangential acceleration is equal to r multiplied by alpha. So r multiplied by 0 is equal to 0. Then A tangential is equal to 0. This doesn't mean that the particle doesn't undergo acceleration, because we know that whenever we have uniform circular motion, acceleration always exists in the form of normal acceleration. However, tangential acceleration may exist or no. This depends whether the speed varies or not. Okay, so in this case we have normal acceleration, but we don't have tangential acceleration. Now in number 6, they are telling me determine the value of the acceleration, and by the value they mean the magnitude. So by the value they mean the magnitude. So here, because we are in the circular motion, we have the acceleration, and this is the total or linear acceleration. We know that A represented in the Frenet basis is given by an multiplied by the unit vector un plus at multiplied by ut. So in this case, the magnitude of A, for example, can be represented in the Cartesian basis to be A is equal to axi plus ayj, but since we are dealing with circular motion, it's more convenient to represent it in the Frene basis. Since we are interested in the magnitude, then we drop down the vector, and a is given by the square root of an square plus at square. So a is equal to the square root of an square plus at square. The value of at is 0. What about the normal acceleration? Because we have change in direction due to the motion along the circle that an exists. So an is equal to v squared divided by r. So the value of v that I have erased here is given by v is equal to 12.56 meters per second. So 12.56 raised to the power 2 divided by 2. So this is equal to 78. This is a very large number. Okay. Let me check something. Okay. So okay, 78.89 meters per second square. I don't think so. The calculation is correct, but I don't think the answer is reasonable in this case, because the acceleration in this case is very large. So they are telling me that the instant is equal to 1 second, but notice that here v doesn't depend on time, because the type of motion is UCM. Okay, so this is equal to square root of an square, so which is equal to an. Then in this case the value of a due to normal acceleration only is equal to 78.89 meters per second square. So this is it for this exercise. Now in exercise number 31, they are telling me the curvilinear abscess of particle m moving along a circle of radius r is equal to 20 centimeters. So r is equal to 20 centimeters, knowing that centimeters is not a unit of length. In order to convert from centimeters to meters, we divide by 100. Then 20 divided by 100 is equal to 0.2 meters. Now it's convenient to specify the equations related to UCM, UVCM, and its relation between the linear and the angular quantities. So in the case of UCM, we have that theta is equal to omega t plus theta 0, omega is equal to a constant, and alpha is equal to a 0. In the case of UVCM, we have that theta is equal to half alpha t squared plus omega 0 t plus theta 0. Omega is equal to alpha t plus omega 0, and alpha is equal to a constant, in which s is equal to r theta, s is equal to r theta, v is equal to r omega, and alpha is equal to, a tangential is equal to r alpha. Moreover, the normal acceleration is given by v square over r, and in the Frene basis, the magnitude of the acceleration is given by an square plus at square. Okay, so these are all the possible equations that we might face or might use in this exercise. Number 1, they are telling me specify the type of motion. In order to specify the type of motion, we need to have the equation of theta as function of time. Notice that here we have s as function of time, but we can determine theta as function of time because s is equal to r theta, knowing that we are interested in determining theta. So theta is equal to s divided by r, which is 5t plus 2 divided by 0.2. So this consists of two fractions having the same common denominator, 0.2. Then it's given by 5 divided by 0.2 multiplied by t plus 2 divided by 0.2. Then theta is given by 25t plus tan. So theta is equal to 25t plus tan. Now since notice that theta in this case is linear in time. Whenever theta is linear in time, this means that the type of motion is UCM. Verifies the general form theta is equal to omega t plus theta 0. Then the type of motion is UCM. Now in number 2, they are telling you determine the angular displacement during 2 seconds. So the angular displacement means delta angular for theta, which is given by final minus initial. So theta 1 or theta final minus theta initial, say for example. So theta final is the theta computed at t is equal to 2 seconds. So which is equal to 25 multiplied by 2 plus 10, replacing the value of t by 2. So this is equal to 60 radians. Now theta initial is for t is equal to 0, which is given by theta 0. This is theta 0. So which is equal to 10 radians. Now delta theta is equal to 60 minus 10, which is equal to 50 radians. So in this case, delta theta is equal to 50 radians. Now they are telling me then deduce the revolutions accomplished during this duration. So here the number of revolutions, okay, number. So n is equal to delta theta divided by 2 pi. The value of delta theta is given by 50 divided by 2, and the value of pi is given by 3.14. So 50 divided by 2 pi. So let's say revolutions. So n is equal to 50 divided by 2 pi revolutions, and the decimal number of this is given by 7.95, and we know that revolution must be an integer number, so it's given by 7 revolutions. Okay, now in number 3 they are telling me determine the angular speed and deduce the linear one. So let's say since the type of motion is UCM, then we have that theta is omega t plus theta 0. Omega is equal to a constant and alpha is equal to 0, in which the given form is given by theta is equal to 25t plus 10. Then by comparison, comparing linear terms, we can see that omega is equal to 25 radians per second, corresponding for the angular speed. And they are telling me deduce. By deduce, it means that we need to use the previous part. You know that the linear speed and omega are related via the following formula. So V is equal to R omega, then 0.2 multiplied by 25, this is equal to 5 meters per second. So the speed is given by 5 meters per second, and the speed is essential in order to calculate, for example, normal acceleration. So now in number 4 they are telling me to determine the angular acceleration of m. So in this case, angular acceleration is equal to 0. The reason is UCM. They deduce the tangential acceleration, the tangential one. So A tangential is equal to R multiplied by alpha, which is R multiplied by 0, which is equal to 0. So A tangential is equal to 0. This doesn't mean that the particle, it's not being so it doesn't experience an acceleration. It does, because the direction of the velocity changes as the particle moves along a circle. So in part 5, they are asking me about the frequency. We know that omega is equal to 2 pi f, then f is equal to omega over 2 pi. The value of omega is given by 25 divided by 2 pi, so this is hertz. So in the decimal form is given by 3.98 hertz. And the period of the motion of amp, so the period is given by 1 over the frequency, so 1 divided by 3.98. Plugging this fraction on the calculator, then it's given by 0.25 seconds. So the period is equal to 0.25 seconds. So that's it for exercise number 31. As for exercise 32, a particle A moves along a circular trajectory of radius r is equal to 1 meters. The curvilinear abscissa, so curvilinear represents S, is given by this. Let me write on the scratch the equations of UCM and UVCM. So theta is equal to omega t plus theta 0. Omega is equal to constant and alpha is equal to 0. Whereas for the case of UVCM, we have that theta is equal to half alpha t square plus omega 0 t plus theta 0. Omega is equal to alpha t plus omega 0, and alpha is equal to a constant. We have that S is equal to r theta, V is equal to r omega, A tangential is equal to r alpha. Moreover, we have that A is equal to square root of an square plus at square, in which an is equal to v square divided by r. Now calculate the curvilinear abscissa of ab and adjacent t is equal to 2 seconds. This is straightforward. Replace the value of t by 2. So s as function of t is equal to 2 seconds is equal to 2 plus 4 multiplied by 2 plus 1. Plugging this polynomial on the calculator, or the algebraic expression. So this is given by 17, and s, recall that it is expressed in meters. So s is equal to 17 meters. Now in number 2, they are telling me calculate the number of revolutions, which is given by n delta theta over 2 pi. In order to determine n, we need to determine delta theta, accomplished by m during these 2 seconds. So we need to determine delta theta in these 2 seconds. There is another way to calculate n. There is another formula, is dividing s by the circumference, which is 2 pi r. So, but let's do it this way by calculating delta theta. So we don't have theta, we have s. So s and theta are related via the following formula. S is equal to r theta. So theta is equal to s divided by r, which is equal to 2t squared plus 4t plus 1. Eventually r is given by 1, so this is indeed theta. So theta is equal to 2t squared plus 4t plus 1. Now delta theta is theta final minus theta initial. So theta initial corresponds for theta 0, which is equal to 1. Now it's left to calculate theta final corresponding for theta t is equal to 2 seconds. And this is given by, so okay, now replacing the value of t by 2, this is given by 17 radians. So delta theta is equal to 17 minus 1, which is equal to 16 radians. Now 16 divided by 2 pi, so this is the number of revolutions. Now the decimal value of this is given by almost 2.54, and the revolutions is given by integer number, so to almost complete 2 revolutions, okay? Now in number 3 they are telling me to calculate the angular speed. So since so the angular speed can be determined by justifying the type of motion. So since s is equal, since theta is equal to 2t to the power 2 plus 4t plus 1 verifies the general form. So whenever the angular position is quadratic in time, this means that the type of motion is UVCM. Verifies the general form theta is equal to half alpha t square plus omega 0 t plus theta 0. Then the type of motion is UVCM, and in this case we can use the following equations. And the given form is given by theta is equal to 2t squared plus 4t plus 1. So we are interested in determining the angular speed at any instant, which is omega. In order to do so, we need to determine alpha and omega 0 separately. So by comparison, we have that half alpha is equal to 2, which means that alpha is equal to 4 radians per second square. As for omega 0, comparing linear terms, we have that omega 0 is equal to 4 radians per second. In this case, omega is equal to 4t plus 4. Then deduce the linear one, and by deduce it means that we need to see the previous part. We know that the linear one and the angular one are related by a radius. So simply v is equal to r omega, which is equal to 1 multiplied by 4t plus 4, which is equal to 4t plus 4. Then v is equal to 4t plus 4, the speed as function of time. Now in part 4 they are telling me to determine the angular acceleration. So notice that we have already discussed the angular acceleration, and it's given by 4 radians per second square. And in order to deduce the tangential acceleration, angular and tangential acceleration are related by a radius. So at is equal to r alpha, then 1 multiplied by 4, which is equal to 4 meters per second square. Then a tangential is equal to 4 meters per second square. So that's it for me in this video, guys. See you soon in another one.